Hey everyone, welcome back to Cybernetters. I'm Andrew Yick, and today we're diving into systemd and software installation in Unix and Linux, which is a crucial topic for modern system administration. So, systemd is like the engine behind your system's boot process and service management. It replaces the older init systems by parallelizing startup, handling service dependencies, and managing everything from network connections to logins. In this session, we will break down how systemd works, how to install and manage software efficiently, whether you're compiling from source or using packet managers, and why mastering these tools is an essential for keeping your system running smoothly. By the end of this lesson, you have a more clear understanding of how to control system services, configure the boot process, and streamline these software installations. Let's jump right in. Let's look at how Unix and Linux actually boots up. So when you power on your machine, the firmware, the BIOS, or the UEFI, it kicks in and decides which device to boot from. Once it figures that out, it hands control to the bootloader, which is often GRUB. GRUB then loads the kernel you selected or the default one and places it into memory. After the kernel initializes and sets up hardware drivers, it mounts the root file system. At that point, the kernel starts PID1, which is either init or systemd. That is the first user space process. So think of it as the master controller that will start all other system services. Finally, once those startup scripts are run and the system services are active, you'll see a login prompt or a graphical login screen waiting for you. So from the power on to a fully running system, the diagram shown here shows that every stage in that chain of events. So this slide kind of focuses in on how the system transitions from firmware to a fully running OS. So when you run or when you power on, the BIOS or the UEFI initializes the hardware, then hands control the bootloader, which is often GRUB. The bootloader's job is to locate and load the kernel into memory. And once the kernel starts, it detects the hardware, mounts the root file system, and spawns the init process. These days, it's usually systemd. The process then kicks off all the other services, which is the networking or logging, etc., stuff like that, until the system is ready for a user to log in. Basically, it's a chain of hands-off from firmware to a bootloader to a kernel and then to a user space. All right, so let's talk about GRUB, which is the Grand Unified Bootloader. So essentially, it's the middleman between your firmware and the Linux kernel. It loads the kernel into memory and can pass along important parameters like which run level or which root partition to use. GRUB also supports multi-boot setups, meaning you can choose between different operating systems at startup, which is handy if you dual boot Linux and Windows, for example, which is originally designed to work with GPT partitioning and replace older bootloaders that only supported MBR. If you ever need to adjust boot order or tweak kernel parameters, you'll find grub's config in bootgrubgrub.conf or sometimes boot grub2 grub.cfg on newer systems. Just remember to back it up before making changes. Alright, so let's talk about GRUB2, which is the newer generation of the GRUB bootloader. Its main configuration file is located at boot grub.cfg, but you typically don't edit that file directly. Instead, you make changes in etc default grub or place additional configuration snippets in etc default grubd. So afterwards, you run grub2 dot or dash mkconfig to regenerate the final config, which is then written to boot grub grub.cfg. That way, you can add or remove device drivers, tweak kernel parameters, or set advanced boot options without messing up the core config. And if you need some advanced troubleshooting, press C at the boot menu. That drops you to the grub command line environment where you can manually load the kernel, set parameters, or inspect your system's boot setup. It is a powerful safety net when things go wrong. So once a kernel is up and running, it hands off control to a program called init, or on a modern system, systemd. This is where the user space really starts. So traditionally, the init come from system V, and it used run levels to manage which services got started. Now, most Linux distros use system D, which can start multiple services in parallel, and they can manage dependencies more efficiently. So if you've ever seen systemctl commands, that's system D in action. At this stage, the system checks the integrity of the file system using fsck, which mounts local disk and it sets up paging. It also cleans up the leftover files, which starts critical services like quotas, mails, and network daemons, and finally gets the machine ready for user logins. Basically, everything beyond the kernel, like networking, logging, and user authentication, starts here. Now let's talk about run levels, which is an older concept from the system V init days, where each run level defines which services and daemons are active. For instance, a run level 3 might have a multi-user console cable, while a run level 5 usually means a graphical environment. There are 7 standard run levels, 0 to 6. You can use the run level command to see which one you're in, and then init run level or telnet run level to switch. In older systems, the default run level is set in SC tab with a line like ID colon 5 colon init default colon, which boots the system straight into level 5. Note that BSD systems don't use run levels at all. They have their own startup mechanisms. And these days, System SD has largely replaced run levels with targets, but understanding run levels is still useful for working on legacy systems for certification exams. So here's a quick rundown of the standard System V run levels that you'll see on these legacy Linux systems. So 0 means the power down state, which means the system is halted. 1 means the system administration or the single user mode, which is often used for maintenance. The run level 2 is for basic multi-user mode, or no networking on some distros. And then run level 3 has the remote file sharing state, which is typically with full networking enabled. The 4 is not commonly used, but it's reserved for custom tasks. The run level 5 is the firmware or graphical console mode on many Linux systems, though it's technically for some hardware tasks. And the last but sixth run level is for shutdown and reboot states, which is used to restart the system. So as you can see, these run levels tell the systems which services to start or kill. And remember with System D, we use targets instead of run levels, but it's still good to know these for older distros or troubleshooting in general. Let's talk about runtime configuration scripts in a classic SysV Init setup. Each run level has a corresponding directory, like RC3D or RC5D, that contains symbolic links to the actual startup and shutdown scripts found in etc initd. So here's how it generally works. S stands for starts. When moving up to a higher run level, the system runs S scripts in ascending numerical order, like S10 network before S20 NFS. K stands for kill. When moving down to a lower run level, it runs the K scripts in descending order with the argument stop, which ensures the services are shut down gracefully. This mechanism helps SysV Init manage which services should start or stop at each run level. Modern systems usually use System D, but if you're dealing with older distros, you'll still see these directories in action. Now let's talk about systemd, the modern replacement for the old SysV Init system. It speeds up boot times by starting services in parallel and managing the dependencies automatically. It also includes journald for logging and tools like networkd and login to handle network connections and user sessions. Under the hood, systemd uses units to represent service, sockets, device, and more. These are typically stored in lib systemd system or etc systemd system. Instead of run level, systemd has targets like power off targets, which is equivalent to run level 0, reboot target, which is 6, rescue target for 1, multi-user target for 3, and graphical target for 5. So if you have ever used systemctl, you have seen systemd in action. So let's switch gears to the Unix software installation. There are two main ways that software is distributed. The first one is using source code distribution, which you get the raw code and you compile it yourself. This is super flexible. You can tweak compile options or optimize for specific hardware. But it does mean you need a compiler and the right libraries installed. And then you have the pre-compiled package distribution, which is the plug and play approach kind of. You download a package like RPM or DAB and install it directly. It's faster, but you're limited to what the package maintainer has provided. One big challenge is dependencies. Sometimes installing one program requires a whole chain of others, like a library or another tool. Historically, that could be a nightmare, but modern package managers handle most of the heavy lifting. So whether you're compiling from source or installing a package, understanding these approaches and how to manage dependency is key to keeping your Unix system up to date and running smoothly. All right, so let's talk about compiling software from source. It's the most flexible option since you can customize compilation for your hardware or preferences. But you need a compiler or any support libraries the program relies on. Typically, you run something like configure, which checks your system for the required libraries and set up a make file, make, which compiles the software, and make install, which installs the compiled program onto your system. Always read the README to see if there's any special instructions or dependencies you need to install first. If the software depends on other packages, you need to hunt those down manually, unless they're bundled. And finally, watch out for licensing issues because some components can't be shipped in a single package due to licensing restrictions. So you might have to download them separately. When you download the source code for Unix, it usually comes in a tarball, which is short for tape archive. Essentially, it's a single file bundling all of the source files together, which is often compressed with gzip or bzip. So to install from a tarball, you must first uncompress it using tools like gunzip or bunzip. Then you extract it using a tar command. For example, if it's gzipped, you might do something like tar-zxvf file name tar.gz. This unzips, extracts, and shows progress and reads a file, and the order of these switches matters. So after that, you can usually run the classic slash configure make install sequence. So a tarball is just a convenient bundle of file compressed to save space. Once you unpack it, you're ready to configure and compile your software. So now let's talk about the packages and the ports collection, which are two ways to install software without compiling everything from scratch. So the ports collection is popular on BSD systems. It automates downloading source code, compiling it onto your machine, and handling dependencies behind the scenes. You get the benefits of a custom build without the manual hassle. And then for packages, on the other hand, are precompiled for a specific architecture like x86. On Linux, you might see .rpm for Red Hat and .deb for Debian-based systems. Tools like yum, DNF, apt, or pkg on BSD automate the entire process. They'll fetch the package, install it, and manage dependencies using online repositories. It makes installing software much simpler, especially if you don't need the flexibility of compiling for source. Just pick your package manager, run the install command, and let it handle the rest. All right, let's talk about modular kernels. So in Unix, device drivers are often built right into the kernel, which can limit hardware compatibility. If you want to support new hardware, you have to go and recompile the kernel with the additional driver code. This can be a bit of a headache, and if the driver code is poorly written, then you can introduce system instability or security holes. So always check the hardware compatibility list before you make changes. A modular kernel can load and unload drivers at runtime, which is super convenient, but you still need to verify that those drivers are well tested and safe. So in short, modular kernels make your life easier, but they also require you to be careful about what you add to your system core. Let's talk about configuring and building kernels. So first off, you need to install the kernel sources and any compilers or not libraries you need. Then back up your current configuration files, just in case you need to revert. Next comes the configuration step. You might use a command line tool, a menu-based interface, or even a script that asks questions about which features you want. Once that's set, you compile and link the kernel, which can take a while depending on your hardware. Finally, install and test your new kernel. You'll copy it into your boot directory, update your bootloader config, and keep a backup of your old known good kernel just in case something goes wrong. That way, you can always roll back to a working setup. Essentially, it's about customizing your kernel for needs while keeping a safety net handy. And that wraps up our deep dive into systemd and software installation in Unix and Linux. We covered everything from how systemd replaces older init systems and the ins and outs of compiling software and managing packets. Understanding these concepts is key to running a stable and efficient Unix system. So now, if you want to test your knowledge, head over to cybernetters.net and we've got quizzes on each topics to help reinforce what you learned today. Thanks for watching, and as always, stay secure and keep learning of Cybernetters. See you in the next one.